Well, we're on the home stretch. 3 weeks left. That's it. So 15 days. I got a little more info about our final exam. The folks said it needed to be during just our class period because I don't know, because that's what they wanted us to do. So, but I want to give you extra time and I really don't want to split it over 2 days. So why don't you let me know if, just think about taking it during our regular class time. And if you'd like to extend it, can you extend it, either start a little early or stay a little late? And if neither one of those will work for you, I think what I'd rather do is kind of work it out individually so that the people that can't make that schedule can come at a different time rather than trying to split it over 2 days for everybody. I'd rather have everybody just sit down and take it, at one time. So you can think about what will fit best into your schedule. I don't know. It's not, you guys probably heard that some classes got extended an extra 2 weeks. And because of that, some people are going to have class. And so if you're going to have class at 10 o'clock, then let me know if there's a conflict and we'll work around it. Sound okay? Okay. So here is the rest of the calendar. Right, I put everything should be up now for you. So here's our last 3 weeks, and this is just our regular class time from 8 to 10. But you're certainly welcome to go, till 11, so you can extend it an hour on the back end, or you can extend it, an hour on the front end if that works for you, or if nothing works, we'll split it over 2 days for you rather than splitting it for everybody. We're going to look at the rest of 11.2 today. We're going to talk about how we know if a series converges or not. And it turns out that there's 3, 4, 5, 6, 7, so 5 sections of ways that you can figure that out. It's a lot like solving integrals. Different series use different tricks or techniques. We're not going to look at them all. We're going to see how far we get. 7 is that they're all mixed up, and I don't know if we'll get far enough with enough techniques that we can look at 7, or if 7's just going to be a reach for us because we haven't spent enough time with the individual techniques. Either way, we'll do 11.3 for sure, and probably 11.4. If you're far enough ahead of everybody that you're already starting some homework problems on 11.7, then that won't hurt you, but be aware that I might just skip that section. Okay, I might skip 11.7. And then we have 2 weeks to do sort of one of my favorite topics in Calc 2. It's called Power Series and Taylor Series. And I think you guys will really like that one. So we're going to wrap it up with 8, 9, 10, 11. 10 and 11 are kind of the same thing. So it's really just 3 sections left, okay, after we get through this testing series. That is there goes my phone. 1 sec, series is trying to talk to me. All right, questions about the calendar? Okay, seeing none, then this is how the game works. I give you a formula, most likely, for a sequence of numbers, and then I try to sum up those numbers in a series and ask you what's the sum. So it depends, I guess, on where the numbers of the sequence are going. If they're getting bigger and bigger, and I add up an infinite list of bigger and bigger things, then the sum is just going to get bigger and bigger. That's pretty straightforward. And so we would say it diverges or goes off to infinity. If the terms themselves are getting smaller and smaller, then we're adding up infinitely many, infinitely small things. Okay, well, that's interesting. Infinitely many sounds like it should get bigger and bigger, but infinitely small sounds like I'm not adding anything on after a while, in which case maybe it actually goes to a number. And that's the race. The race is, are these terms getting smaller fast enough so that when I add up infinitely many of them, I'm really adding nothing? Or are these terms still big enough that as I add infinitely many of them, I'm still adding up more and more stuff, and the sum runs off to infinity? Okay, that's really what this whole thing comes down to. It's a lot like a L'Hopital race, right? We're adding up infinitely many things, but those things are getting infinitely small. And the question is, who wins, right? And how do we know? And then how do we prove it? Okay, and that's what these 6 sections are all about. And I guess when I teach this, it's actually really hard because we just play this game. It's just a math game. There's no real motivation for it in the real world or anything yet. We haven't seen an application of where we might want to add up the terms of a sequence in a series. But it turns out there are a lot of them. And that's kind of why I like that section 11.8, because that's like our first real application of when are we going to use this. And we're only going to get to look at a couple of applications because we don't have a lot of time. But it turns out we do this quite a bit, mostly in other math classes, but sometimes in physics and engineering and business as well. Okay, so that's the game. So you say, I'm adding up all these terms. So what I would do first is I would make a list of some of these terms. I would write it, if it's in summation notation, I would write it in an expanded form like this so that I can see what the terms are. In fact, sometimes this isn't real clear either. 10/3, which is, sometimes it's more clear if you put them in decimal, because then you can see if they're going up and down and where they're going. So, and of course, I don't want to compute all these by hand, but if you did, you'd put n equals 1 in and get 1/2. And then n equals 2 and get 1/4. And then n equals 3 and get 1/8. So what I've got is a 1/2 plus a 1/4 plus an 1/8 plus a 1/16 plus a 32nd. This has a chance to converge because the terms are getting smaller, right? And so we want to know if it is, what's it getting closer to? And most of the time, I don't usually do that by hand. This is an easy formula. Most of the time, what I would do is I would just put it in Desmos. So let me jump over to Desmos. We just go to Desmos. Where is it? Here it is. I sort of got this started. Oops. What happened? Oh. I'd already put a few things in this morning, so I was a little bit ahead of you. So I would get a little Desmos file that looks like this. You can either build it every time or you can have it pre-built and just save it. And so what I'm going to do is I'm going to plug in the numbers 1 to 100. We're not going to go all the way to infinity. We're going to hope that we can see what's happening in the first 100 terms because, of course, Desmos can't go all the way to infinity. So if you can't kind of guess where it's going by then, you're going to need to use hey, one of the techniques from 11, 3, 4, 5, 6, or 7. Here's the formula for the nth term. And here's the formula for the nth partial sum. And then I'm going to plot the points and the sums. Okay, so what was ours? It was 1 over 2 to the n. So you're going to put in 1 over 2 to the n. And you're going to say, okay, the terms are red. So the terms are 1/2, 1/4, an 1/8, the 16th, the 32nd. And you can see that the terms are getting smaller and smaller. So we might ask, what's the limit of the sequence as n goes to infinity? So if we were to do that, you'd write something like this. You'd write, what's the limit as n goes to infinity of a sub n? In other words, where are the terms going? And you'd say where? You'd say, somebody
0.
say 0, right on. They're going to 0. Okay, and so if you substitute the formula in there, of course you can see it. Notice that I'm talking about now, where are the terms going, not where are the sums going. So check it out what's happening. I'm going 1 divided by something really big. 1 divided by something really big is 0, yeah? Okay, so where are the terms going? here's something, we're going to develop a bunch of tests. The tests are going to tell us whether or not it converges or diverges. And one of our very first tests is called the simple divergence test. And it goes something like this. If the terms don't go to 0, then it diverges. Meaning if these terms are getting bigger and bigger and bigger and bigger, I add them up, then I'm going to get something that goes to infinity. In fact, it's even stronger than that. If these terms are going and going and going and going, but leveling out at, say, 5, but then I add up infinitely many 5s, I'm still going to go to infinity. So essentially, the simple divergence test says this. Take a look at the terms of the sequence. If they're not going to 0, then it does not converge. Good with, we happy? Okay, beautiful. So this one has a chance. Now, the converse of that is not necessarily true, meaning that if the terms go to 0, okay, it still doesn't have to converge, which is kind of interesting. So it'll only tell you if it diverges. So this one has a chance to converge. So then we look at it a little bit more closely and check it out. Here's the first one. What is that? That's 1/2, because that's 1/2 plus nothing. This is 3/4, because that's a half plus a quarter. This is 7/8, because that's a half plus a quarter plus an eighth. And so I'm looking at the partial sums, and as I take the sums, as I take the sums over more and more terms, notice that they seem to be leveling off, and you would guess that they're leveling off where? Looks like
around 1.
Looks like 1 to me. Okay, so now I'm asking, what's the limit as n goes to infinity of the sum, pretty ugly sum, of the sum I equals 1 to n. Notice that I changed my index to I because I'm going to go out to n, and then I'm going to let n go to infinity. So here I had the upper limit being infinity. It's kind of like an improper integral. And I like n to go to infinity. You could have just put a t here and made that a t and left this an n. If you like the terms themselves to be called n, I like the terms to be called I. It doesn't make any difference, right? You can use whatever letters you like. And now I'm saying 1 over 2 to the I. So I'm saying, where are these partial sums going? Right? So it's the sum of the first 1 term, the first 2 terms, the first 3 terms, the first n terms. One of the nice things is that if you can find a formula for this part, then you can just take the limit of that formula. Okay, we already saw an example of this. This is maybe the first trick that we can use to find a sum. Let me jump down here and show you that example. We took the limit as n goes to infinity of the sum I equals 1 to n of just the i's. Okay, and you said, oh, I know where this goes. I'm adding 1 plus 2 plus 3 plus 4 plus 5 plus 6. It's going to infinity, isn't it? Okay, but the way that we could do that is we could find a formula for this part. In fact, we know a formula for that part. What is it? Add up the first n integers.
N times n plus 1 divided by 2.
N times n plus 1 divided by 2. Now, to find the limit of my sum, I just take my limit like I would before. Notice that the numerator's got a bunch of stuff in it, getting bigger and bigger. The denominator just has a 2, so this goes to infinity. We could also use the simple divergence test here. We could look at the terms themselves. What are the terms doing? Getting bigger, 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 bigger. So what happens? The sum of all those terms goes to infinity. Now, if you're trying to find the limit of a sum, and you can find this formula, the formula for the nth partial sum, then you can just take the limit and you're done. Seems like that should be a pretty straightforward thing to do. We did it for this one. The problem is that it's hard, okay? In fact, usually we can't find this formula. Okay, so that's the first thing we do. If you can find a formula, find the formula. You might have noticed on the homework, it was a little weird. It would say things like, if we know the formula is this, then where is it going? And the reason on the homework why it gave you those formulas is because they're really hard to come up with. Okay, remember when we were coming up with this formula, we had to guess it, right? And then we had to prove it by induction. So this technique doesn't work so good. So the question is, how do we know what this one's doing, right? That's the big question. So the next thing I would probably do with this is I would write it out like this: 1/2 plus 1/4 plus 1/8 plus ... so that I can kind of see what it's doing. I'm going to check that the terms are getting smaller and smaller. And then I'm going to guess that this is going to, I don't know, where do you think it's going to? Sometimes it's nice to write this. The limit as n goes to infinity of the partial sums. So what are the sums? The sums are this sequence, right? 1/2, 1/2 plus 1/4, 3/4, 1/2 plus 1/4 plus 1/8, 7/8, 1/2 plus 1/4 plus 1/8 plus 1/16, 15/16. So what we're saying is, where is that sequence going? Where is that sequence of partial sums going? And it looks like we can figure that out, yeah?
Yeah.
It's going to 1, isn't it?
Yeah.
Okay. So these are all sort of tricks and techniques for sort of figuring out where something is heading. I would say that we've provided pretty strong evidence that this is going to 1, but I don't know that we actually have a foolproof that everybody is going to be convinced of. Okay, so we've provided pretty strong evidence, but we haven't, I don't think we've convinced everybody yet. So we're still going to look for a stronger argument that says this goes to 1. But I think we've got a pretty good idea that it is going to 1. So your job on these is to, 1, guess where it's going, okay? And then after you've guessed where it's going, somebody joined us, or maybe left, I don't know. After you've guessed where it's going, then you have to provide evidence. And so, here's some pretty good evidence. This looks like it's going to 1 to me. The graph is pretty good evidence. And so those are all things that you can certainly do to provide a justification for your guess. I would say a graph is a good start, but it's not the whole answer. So then we'd have to come up with a stronger argument. Good so far? Okay, I'm getting some nods. Beautiful. Let's look at these other ones before we go about trying to prove this really goes where we say it's going. Here's another one right here. 3 to the n plus 1 minus 2 to the n. Minus 2 to the n sounds like it's going to make a minus. When n is 1, you're going to get negative. When n is 2, you're going to get positive. So this is an alternating series. So it's going to go up and down and up and down, just like this one does. I've started at 5. I take away 3 1/3. I add a little bit more. I subtract a little bit more. I'm adding some. I'm subtracting some. I'm adding some. I'm subtracting some. So it sort of begs the question, am I adding and subtracting about the same amount? Because then it would probably go to 0. Or am I adding more than I'm taking away? And if I'm adding more and more, then it sounds like it might run off to infinity. But if all of these terms are getting smaller, 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 then the amount I'm adding and subtracting, and then adding and subtracting, itself is getting smaller, in which case it very well might converge. Okay, so you just got to get your head wrapped around it. If it's in this form, then you have to do this part. you have to write your own formula like this. If it's in this form, then sometimes it's hard to see the terms themselves. So you should probably expand a few of the terms. I can tell you that it's much easier to plug in 1 and then 2 and then 3 and then 4 and get a list of the terms than it is to figure out what the formula is, right, if you weren't given the formula. Because here you have to kind of guess the pattern and then write a formula for the pattern. So if it's in this form, you write the formula first. If it's in this form, you probably expand the terms first so that you can see it. I'm going to just expand all the terms of this using Desmos because it's just easier for me. You can certainly do it by hand as well. But I'm kind of thinking Desmos is easier. So what do we got? We got 3 to the n plus 1 up here. And we got minus 2 to the n down here. Oops, I think I need maybe a paren. Minus 2 to the n down here. So what's happening, right? Pretty hard to tell. It's like craziness. What's happening? Well, whatever's happening, it's going really fast, isn't it? So you might have to, like normal, adjust your window so that you can kind of see what's going on. I'm going to say, I don't need too many terms because this seems to be happening pretty fast. So let's go 0 to 10 terms, maybe. Maybe we'll go to 20 terms. Okay. And then you're saying, wow, it's getting big and small really fast. Maybe that's enough that you don't have to play with this anymore.
I had a quick question.
Yes.
Is the +1 supposed to be in the exponent, or is it just on the end? Like you have?
That, I think, is in the exponent in this case. But it certainly would be a good question on what if it's on the end, right? In other words, you get a different sequence, and then you'd have to ask that question. This one was in the exponent. So I've got to put it in the exponent where it belongs. Oops. Why won't it let me type up there? Okay. Here, we'll do this. Now it'll let me type up there. Okay, and guess what? Didn't look like it made a lot of difference in this case, did it? Okay, so what are the red ones? The red ones are the terms. So what are the terms doing? They're getting
bigger
and bigger, yeah. Now you could say, well, really one's big, one's small, one's big, one's small, right? And so maybe what we would look at is, maybe we would want to look at the absolute value of the terms, the absolute value of the terms, and make them all big. Well, certainly if the terms are getting bigger and bigger and bigger, then we're adding and subtracting more every time. Sounds like it's going to diverge. So the question is, if the absolute value of an alternating series goes somewhere, does the series go to the same place? And the answer is yes. I think we already saw that. At least we saw it in the case of it going to 0. So when you get an alternating series, you should consider the absolute value of the terms, and then you don't have to worry about the alternating part. This has a name. I think it's called the something, something, something absolute value theorem. Okay, it's probably in section 7. All right, so there go the terms. All right, so now what's happening with the sums? All right, so now we'll take a look at the sums. Sometimes it's confusing for me to see, them both at the same time. So you can turn one off and then the other. What are the sums doing? Negative, positive, bigger, 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 diverges. Are we happy? I think you can see this diverges. A proof that this diverges would be, look at the terms themselves. If the terms themselves are not going to 0, then it diverges. And then we would say it diverges by what we call the simple divergence test. And of course, to be thorough, we would have to prove that the simple divergence test is actually a real test. In other words, that that statement is a true statement. So you'd have to prove that theorem first, and then we would use it. What we generally do when we have lots and lots of time, as in if we took a whole class and it was just devoted to just this, right? So we had a whole semester to look at these. We would first just kind of practice looking at them. Then we would practice using the tests. And then once we were comfortable using the test, then we go back and prove the test really does what we say it does. Okay, so that's that one. I say diverges. And now we're to the last one. So on the last one, right, on the last one, we don't have a formula. So I can't just jam it in. I can't just jam it into Desmos. I'm going to have to write my formula. So I have to deal with this part right here. Right? So how do we do it? Right? I don't know how you do it. You're going to have to figure out what the formula is for the dot, dot, dot. So you look at what's happening and see if you can figure it out. And sometimes, I don't know, sometimes it's easy to see what's happening, and sometimes it's harder to see what's happening. And I can't give you any process or procedure that you can use every time. You simply have to look at this and figure it out. Okay, and so sometimes you'll see them right away, and sometimes you won't. And this is a matter of just numeracy and experience and luck. All right, so give me a formula. What's it look like the bottom's doing?
The bottom is the previous number multiplied by the next number.
Oh boy. So you've got two ways that you can write this formula down. One is you can do it recursively, like you were saying. Try to figure out the next one based on the one before it. Or you can figure it out explicitly. So I was starting with an explicit formula. You were starting with a recursive formula. And you were telling me something like this. The bottom, right, gets multiplied by 3 is what I think you were trying to tell me. Take the previous one, multiply the bottom by 3. Okay. Well, keep going. I either need this formula or this formula. How do I get the tops?
Multiply by 2.
Multiply by 2. Looks like that's close.
And then you just make it the 2/3 negative, so it flips every time.
Ah, all right. Multiply it by negative 2/3. And then you got to tell me one more thing if it's recursive.
N equals 5.
Yeah, n equals 5 here. No. Where do we start? You got to tell me where we start, because I got to know what to multiply by the first 2/3.
5.
5. Not n equals 5, but
A1.
A1 equals 5, yeah? So I start at 5, I multiply by minus 2/3, I multiply by minus 2/3, I multiply by minus 2/3. Sweet. Here is a recursive definition. I got some good news and bad news. You can now produce all the terms using this. The bad news is I still can't type it into Desmos because Desmos doesn't do recursion. Sometimes it's easier to write the recursive formula than the explicit one. But it's generally easier to write the explicit one if you know something about what's going on, meaning sometimes it's easier to write the recursive one first and then the explicit one. But we still need an explicit formula. I think, though, we can see where these terms are going. If I keep multiplying by 2/3 and multiplying by 2/3 and multiplying by 2/3, what's happening here? The terms are getting bigger, 2/3.
Smaller, sorry.
There you go, 2/3. If I take 2/3 of something,
Yeah.
and then I take 2/3 of something, and then I take 2/3 of something, sound smaller?
Yeah.
Smaller, 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 smaller. They're getting smaller. So if I said that the limit as n goes to infinity of a sub n, you say it goes to where? 0,
0.
0. Because we can consider the limit as n goes to infinity of the absolute value of a sub n, which for sure goes to 0. So if the absolute value of the terms is going to 0, then the terms go to 0. And since the terms are going to 0, if I add them all up, I have a chance. I have a chance for it to converge. Doesn't mean it's guaranteed to converge, because, but it might converge. Okay. However, if the terms don't go to 0, then it does not converge, and we can say it diverges, and we're done. Okay, so we got to keep going because the terms are going to 0. So we still got to investigate what's going on here. Does this sum go somewhere or not? All right, so now I need an explicit formula. Hit me with it. How do I get the nth term directly? Think about what we're doing here. We're multiplying by 2/3. Then we're multiplying by 2/3 again. Then we're multiplying by 2/3 again. Then we're multiplying by 2/3 a bunch of times. What's the formula for multiplying by 2/3 a bunch of times? Something like this?
Mm-hmm.
Except that's not quite right, because the very first term doesn't get multiplied by 2/3. So what if I do this? Then when I stick in a 1, I got 2/3 to the 0, which is equal to 1. But that's not quite it either, because it's supposed to start where?
At 5. So
At 5. So try this formula. Take 5, and for the very first term, don't multiply by 2/3, multiply by 1. For the second one, then go 2 minus 1, multiply it by 2/3, minus 2/3 one time. Then for the third one, take 5, multiply by minus 2/3 twice, better known as 3 minus 1. Is this it? I think this is the formula. So the very first thing that we would need to do is to find the formula, right, for the nth term. And then we're going to say, where's this formula going? We already know it's going to 0. We checked it down here. So now we want to know, where are the partial sums going? In other words, what's the sum of the sequence if I add all these up? So now we're going to look at the limit as n goes to infinity of the partial sums. So we're going to look at the sum of the first term, which is 5, and then the second one, which is 5 minus 10/3, and then the third one, which is 5 minus 10/3 plus 29ths. Okay, and again, we might want to do that. In Desmos first time. So now that we have a formula, we should be able to put it in here without too much trouble. I've got 5 times minus 2/3, right, to the n minus 1 power. Okay, well, my terms are not getting bigger. That's good. So now I'm going to readjust here. I'd like my y-axis to be small. So how about minus 1 to 1 or something like that? Maybe that's too small because it started up here, yeah? Okay, there, I could zoom out and see it. So look at what's happening. It's looking to me like, oh, those are the sums. Here are the terms. Oh, those are the absolute value of the terms. Oops. Here are the terms. Okay, so what are the terms doing? And you say, looks like they're going to where?
0.
0. That's good. Because if they don't go to 0, the sum does not converge. Okay, now let's look at the sums. So where are the sums going? Here's the first one. There's 5. There's 5 minus 3 1/3, okay, which is 1 2/3. There's this one and that one and this one, the first 3 terms. Now I'm at 3.89999. And I'm thankful, because of all these little fractions, to have Desmos added up for me. And it sure looks to me like it's going to where?
3.
Sure looks like it's going to 3. So we would say the limit of the partial sums, our guess is that the limit of the partial sums is going to be equal to 3. Okay, how come? Picture. That's a good start, but not a very good proof. Okay, so how do we prove it? That's the big question. In other words, how do we get this number given this info? Yeah, and I mean, that's not obvious. Unfortunately, it's not obvious.
It's really, this one's kind of funky because you've got positive terms and you've got negative terms. And then the negative terms end up being larger than the positive ones.
Yeah, a little bit, right? But they're all going to 0. The positive and negatives are going to 0. So it bounces back and forth, doesn't it?
Yeah, it oscillates too.
Yeah. Yeah. Okay, so the question is, if I give you this, how do you get to this, right? Without just guessing by looking at the graph. That's our next job. The very first thing you should do, though, is what we just did. Write a formula, look at the terms, look in Desmos, guess where it's going. And when you're getting good at that, which I hope you already practiced a little bit, because that was like the homework over the weekend. Now the job is, how do we do this, right? Is there a procedure or a trick or a technique or something? And the answer is, of course there is. We got like 30 pages of book coming in front of us for all kinds of tricks and techniques. Okay. And of course, if you've been with me for a while, then you know that this is where I pause and just blah, blah, blah for a bit, because as soon as I tell you the trick or technique, then I've spoiled the math for you. This is the moment, right? This is the mathematical moment, the question. This is what keeps people doing math stuff, is this question. Because it's not interesting to compute these or prove these once you know the formula. Then you're just using a formula over and over again. What's exciting for math types is figuring this out, right? And as soon as I tell you, then you can't figure it out. You just use it, and using it is boring. It's the figuring it out part when you go, aha, I got it, right? That's the part that's why math types do this, right? And they don't really care that other people have already done it, before them. They just cover up their work and they root around and they fuss with this and they try to figure out what's going on until they can prove it for themselves. And I guess it's that moment of proving it for yourself that is the payoff, right? That's what people love. I've probably told you this, it's like climbing a mountain. There's no real reason to climb up there. And as soon as you get up there, you're just gonna walk back down anyway. But it's that sense of accomplishment that you got up there. And it doesn't really matter if other people have climbed higher mountains or other people have climbed this mountain. It's just the fact that you managed to get yourself up to the top of it on your own, right? That's kind of the exciting part. So of course I'm going to spoil this for you because we have to move on. This is not really the easiest thing, right? If you don't know how to do it, look it up in a book, okay? Or have me tell you. That's the easiest way to kind of solve this problem. And you can get a little bit of an aha from that. But if you sit down to try to figure this out on your own, blank piece of paper, I don't know, maybe 5 minutes, maybe 5 days, maybe 5 years, right? This stuff, right? It's not, there's no guidelines for how to make this happen. You just have to root around with it until you get it, okay? And that's what math types do, right? When they're not teaching classes. Right? I think that's it. Okay, so let's see some stuff. Here's what I want to do. I want to start with an easier one. Would that be okay? Because this one alternates and I don't want to deal with the plus and minus right now. So what I want to do is go back and look at number 1 again. And I want to say, okay, here's number 1. I'm going to copy it down again. Here's number 1. It's the sum n equals, I'm going to write it as I maybe, so it's in the same format. I equals 1 to n as n goes to infinity of 1 over 2 to the n. Okay, which I could probably write in a little bit different form. So I can write the limit as n goes to infinity of the sum I equals 1 to n of 1 times 1/2 to the nth power. So this looks a lot like the last one. Notice, oops, sorry, maybe I should write it like this. I'm going to even change it still. I'm going to write it as 1/2 to the n minus 1 power. So first of all, you should confirm those really are the same, right? If I raise a fraction to a power, I raise the top and bottom to a power. 1 to any power is 1. So the denominator is 2 to the n minus 1. If I multiply it by another 2, I add the exponents. So I get 2 to the n minus 1 plus 1, or 2 to the n. So these are the same. So why write it this way? That's the first question. And the answer is maybe this. What do I get when I put in the first term? Put in 1. I get 1 minus 1 is 0. And I don't multiply by 1/2. The very first term just starts at 1/2. So this turns out to be the first term. Yeah?
Is the sum of a product the product of the sums?
Ooh, good question. And the answer is no. Yeah. We have to explore that some more, but I think no. All right, so what do you do to get the second term? You take the first term and do what? Multiply times 1/2, yes?
Mhm.
1/2 times 1/2 to get a quarter? I'm not getting very many nods from Curtis. He's the one that wanted to do this recursively. There we go. Okay, so how do you get the third term? You take the 1/2 and then you multiply it times 1/2 times 1/2. So when you stick in 3, you get 3 minus 1 or 2, right? So it says take your 1/2, take your first term and multiply it times 1/2 2 more times. And then 3 more times, and 4 more times. And so it turns out that this is a very special series, okay? They don't all work this way, but when they do, we call them geometric series. Geometric series are series that can be built recursively by saying the next term is equal to some starting term. I'm going to call it, what am I going to call it? The book just called it A, but I'm going to call it, okay, I'm just going to call it A. Okay, take some starting term and multiply it times the term, yeah, that's kind of ugly. I'm going to say, I'm trying to get notation here, so when you look in the book, it'll work out good. It'll take the previous term, and multiply it by a ratio. How about that? Where A sub 1 is A. I don't know if that was helpful. Basically what we're saying is, take the previous term and multiply it times a number. Okay. Explicitly, these things look like this. A sub n is equal to a times r to the n minus 1 power. We call these geometric series. So what I'm telling you here is this is a special case. And we wanted to try to prove that the sum of the one we had earlier was 3, and that the sum of this one is 1. Yeah? So the question is, how do we do that? Right? Let me see if we can write it out, because we don't. So I'm going to write the sum. N equals 1 to infinity. A times r to the n minus 1 power. This is our sum that we're interested in. It's equal to this. A plus a times r plus a times r squared plus a times r cubed plus a times r to the 4th plus dot, dot, dot. Now, of course, we could do this with our specific one. I'm going to just use the general formula here. And so the question is, what's happening, right? Can we come up with a formula for this? And the answer is super cool trick. Do you remember old young Gauss when we were adding up an arithmetic sequence where he added it up forward and backward and we ended up with a formula?
Mhm.
You can't hardly forget that. It's a cool trick. Similar trick. Okay, here we go. Check this out. I'm going to call the nth partial sum S sub n, right? How do you get the nth partial sum? You say a plus ar plus ar to the n, ar to the 2 plus dot, 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 a plus ar to the n minus 1. Okay, so I'm going to say, because remember, if we want to find the sum of a series, we're supposed to look at the partial sums. And we're supposed to say, where are the partial sums going? And the sequence of partial sums goes to the limit. So let's write out the nth partial sum. And it looks something like that, I think. Okay, are you ready now? Here comes the cool part. Multiply this by r. Why? I don't know, because it works. Because somebody clever like Gauss thought about it, right? When he was bored in class, because his teacher wasn't going fast enough for him. Here's what we get. I'm going to shift it over a little bit. R times A is AR plus R times the AR is AR squared plus dot, 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 plus AR to the n minus 1 plus the R times the AR to the n minus 1 is AR to the n. So all I did so far is list the partial sums, and then I multiplied both sides by R. And then I just shifted it over because I want to be able to subtract real nice. Okay, you ready? Here comes the subtract real nice. Subtract these. All right, subtract these. What do we got? Let's see, okay, I'm gonna do it this way. S sub n minus R times S sub n, that's what we get here, right? This minus this. Okay, this minus 0, that's A. This minus this, those subtract real nice, they're gone. This minus this, this minus this, this minus this. 0 minus this, that's minus AR to the n. I think we saw this trick maybe once before or something similar when we talked about telescoping series. Or we try to make the middle part of the series go away. Okay, so what are we trying to find? A formula for the nth partial sum so that we can take the limit as n goes to infinity. So I need s of n on one side. So I'm going to factor it out. And just for grins, I'm going to factor out the a on this side too, just for fun. I don't have to, but I am. Divide by 1 minus r. And guess what we have? Looks to me like a formula for the nth partial sum. So maybe what we should do is check to see if this works good, right? Is this even work? We want to look at some example. Yeah, which one should we look at? Let's look at, well, it doesn't matter. We got two good examples going, right? In example 1, a, this was example 1, a was a half, right? And we were multiplying every time by a half. So what we're saying is like the fifth partial sum would be 1/2, 1 minus 1/2 to the fifth over 1 minus 1/2. Okay, well that looks to me like 1 minus a half is a half, and this half will cancel with that half. So I'm left with 1 minus 1 over 2 to the fifth. 2 to the fifth is a 32nd. So that means I should get 31 32nds. And so the question is, what is that? And then I'm hoping that I still have this up on my screen in Desmos so we can check. Which one do I have up? Oops, I changed it. I think you can remember that though. Do you remember that it was 31 32nds? Because what was it going? It was going 1/2, 3/4, 7/8, right? Let's do this one so I don't have to change Desmos over. Okay, this was example 3. In example 3, I was starting at 5, and my ratio was what? I was starting at 5, and my ratio was -2/3. Yeah, I hear Katie mouthing it with her mic off.
Yeah.
Okay, -2/3. Okay, so what would the fifth sum be on this one? It would be 5, 1 minus the -2/3 to the nth power over 1 minus a -2/3. I mean, if our formula is right and all, we should get whatever this is. Oh, I need a fifth.
Can you move your page down?
Yes. I'm just plugging it in, yeah, to see what it's going to go to. This looks like I could make kind of a mistake computing this. So maybe I want to clean it up a little and then just use a calculator or something. That's 3/3 plus 2/3, that's 5/3. So when I flip it over, I get 3/5. The 5s cancel. So I've got 3, 1 minus, and now I've got -2/3 to the fifth. Ugh, that's going to be negative. That makes this positive. 2 to the fifth, I know, that's 32, I think. And 3 to the fifth, I don't know. 81 times 3, 243. And now I maybe need a calculator to finish it off. Okay, so 2, I'm just going to check. 2 to the fifth, that looks good. 3 to the fifth, that also looks good. So now I'm going to see if I can do this. I've got 3 times 1 plus 32 over 243. And I should end up with about 3.395 something. You with me so far?
Oh.
We're just checking to see if this formula that we just came up with is the right formula. And so we're saying the fifth partial sum should be this number. So let's go look and see what Desmos gets when it adds up the first five. Well, let's see. These are the sums. So what does it get for the first one? I went a little bit too far in. 5, right? There's the first one. Here's the second one. Here's the third one. Here's the fourth one. Here's the fifth one. Hey, is that what we got? 3.395. Beautiful. It looks like our formula is working. Yeah, it's giving us the nth partial sum. This is beautiful, right? Because remember what our number one trick was to find the sum? Is to find a formula for the nth sum and then take the limit as n goes to infinity. Do you remember at the very beginning of today, I said, it's hard to find the formula? Yeah, that's what we're just doing. It's hard to find the formula. But I think we found it. Okay, beautiful. So what do? If I want to know what the whole sum is, which is the sum n equals 1 to infinity, right, of my sequence. Where was my sequence of a sub n? I'm just going to write a sub n. Do you want me to write it down again? Let me write it down again. It's on this side. 5 times minus 2/3 to the n minus 1 power, right? Then here's what I'm going to claim this thing goes to. It's going to go to the limit as n goes to infinity of the partial sums. And we know what the partial sums are now because we found a formula for it. It was 5, right, the first term, 1 minus the minus 2/3 to the nth power over 1 minus a minus 2/3. That's a thirds. So if we can find this limit, then we can figure out where everything's going. Well, let's clean it up a little bit. We've got the limit. Holy moly, you got to go faster. Being online doesn't save a lot of time, does it? I still run out of time. Okay, here we go. 1 plus 2/3, that's 5/3. Flip it over, that's 3/5. 3/5 times 5, so 5's cancel. I get a 3. I got a 1 minus 2/3 to the nth power. Okay, so what does that do? I don't know. Looks to me like that's the limit as n goes to infinity. 3 times 1, 3. Notice that when I go 3 times this minus 2/3, that I get an extra 3 in the bottom. Yeah? No, I get 1 less 3 in the bottom. So what does that look like? That looks like minus 2 to the n in the top and 3 to the n minus 1 in the bottom, yeah? I don't know if that's easier or not easier. I know it's easier to pull this out. That part goes to where?
3.
This goes to
3.
3, yeah? So the question is, where does this go? Maybe it's not easier to write it that way. I don't know. It's going to depend on you. I was thinking that for some people that might help. For me, it didn't seem to help. I like writing it like this. 3 times minus 2/3 to the n. So this part goes to 3. This part goes to what? Minus 2/3 to the n.
Okay, well then, maybe 2 to the n. Because there's going to be an exponent on both parts of that fraction. I'd say
Mhm.
that 3 to the end is going to approach infinity faster, so it's going to 0.
It is going to 0. You can think about it this way. What if I take 2/3 of something and then 2/3 of something and then 2/3 of something and then 2/3 of something? Getting smaller, isn't it?
Yeah.
All the way to 0, right on. And 0 times 3 is 0. So all this part goes to where? 0, meaning that the answer is
3.
3. And what did we get in Desmos? 3. Okay, so guess what? After all that work and about an hour and lots of talking, we actually did something a little bit stronger than just saying, looks like it goes to 3. I would argue that we proved that it goes to 3. And I would say that we got a bonus. We got a bonus because we were able to find the formula for the nth partial sum. We were able to find a formula for the nth partial sum. And not only did we do it for this problem, but we did it for all problems that are similar to this one, meaning all series that are called geometric series. If it's in this form, then we got all of them all at once, which is pretty cool because that solved a whole bunch of problems. Of course, it didn't solve every problem in the universe, because if it's not a geometric series, then this isn't the formula for the nth partial sum, in which case we would have to root around to try to find the formula for the nth partial sum so that we can take the limit and see where it's going. And in general, finding this formula, not easy. So what we do is we find it when we can, and if we can't find it, then we do something else, like section 11, 3 or 4 or 5 or 6 or 7. How are we doing so far? Still good? Okay, beautiful. So what do I want to do? What I want to do is go back and prove number 1. Okay, so I'm going to go back and do number 1. We said, where is this going? N equals 1 to infinity of, it was originally written as 1 over 2 to the n. And you said, looks like it's going to 1 to me. Then you give me a table and a list, which is pretty good, Justin. Now we want to prove. So I'm going to argue, if I could find a formula, right? A formula for S of n then S would be equal to the limit as n goes to infinity of my partial sums. This is always true. This is always true. So it's not if I can find it, then the sum is the limit. The sum is always the limit. The question is, can you find the formula for this? Okay, and the answer is not very often, but you can if it's geometric. So not very often, but yes, if geometric series. Okay, and yes, in some other cases too, but always yes if it's a geometric series. All right, so without going back all the way through the details, we recognize that our series here is geometric. Right? Maybe I should write it down first. How do you know it's a geometric series? A geometric series is in this form. A sub n, right, is going to be the first term times some ratio to the n minus 1 power. In other words, I start somewhere and then I multiply it by a number, multiply by the same number, multiply the same number, multiply by the same number. Okay? And if this is the case, this is geometric, then the sum we just found with our little cool formula of multiplying it by r and subtracting, we ended up with a times 1 minus r to the n minus 1 over 1 minus r. So we do know the formula. So all we have to do is take the limit as this formula goes to infinity, as n goes to infinity. So let's see about our example, just as fallen off the page. We've got a sub n is equal to what? The first term is 1/2. The ratio is 1/2 to the n minus 1 power. In other words, in this one, we start at a half, and then we multiply by half. And then we multiply by half again, multiply by half again. So what's the sum? The sum is the first term, 1 minus the ratio to the n minus 1 power over 1 minus the ratio. Well, let's see, 1 minus a half is a half. It cancels with that half. So I can clean this up a little as I'm looking at the limit as n goes to infinity of the partial sums, which is equal to the limit as n goes to infinity. I canceled the halves. I get 1 minus 1/2 to the n minus 1 power. If you still don't like that, you can say, well, the limit of a difference, right, is the difference of the limits. And the limit as n goes to infinity of 1 is equal to 1. And what are we left with? We're left with 1 over 2 to the n minus 1 power. Okay, well, where does 1 over 2 to the n minus 1 go when n goes to infinity?
Goes to
Bottom's getting big, isn't it? Bigger, 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 which means this all goes to
0.
0. And we're left with, bam, sweet. It goes to 1, just like we said. Whew, that was a lot of work. Okay, I got some good news and some bad news. The good news is you can do about 10 more problems on the homework. Because if it turns out to be a geometric series, then you can use what we've been just talking about to figure out where it goes. I got some bad news though. Check it out. Here's a nice one. How about this one? Let's see, I want to give you an example that you might run into in the book. We did this one.
What happens if we did trig in a series?
If you did trig in a series,
If there's trig in a series and it ends up being one of those sums that we can't, there's no formula for it.
like this,
Yeah, one of the funky ones.
yeah, that's a good question. Section 3, 4, 5, 6, 7. We got to keep going. This is definitely not geometric, right? It's not found by taking the previous term and multiplying it by a fraction. So even what would this look like? I mean, what I would do is I would go look at a few terms first, if you had something like this. And then you'd say, I don't know, it's the cosine of n, yeah? Oh my goodness, look what the sum is doing. You think that looks like it's going to a number?
I don't even know where it's going.
It doesn't even look like it's going anywhere, does it? I mean, it looks to me like it's just bouncing all around somewhere between about -1.5 and 1.5. Doesn't look to me like it's going to get to anywhere. In fact, if we wanted to look at the terms, look at what the terms are doing. They're just kind of jumping around, because think of what you're doing. You're taking the cosine of 1 radian, then the cosine of 2 radians, then the cosine of 3 radians, right? So what are you doing? Just going around and around the circle. So it's just bouncing around from numbers between -1 and 1. And when I add up all those numbers from -1 to 1, boom, I just get a bunch of sums that all bounce around. I would say diverges.
It's sort of funny. It kind of looks like if that was a 3D shape and you could imagine like kind of like it was like in the shape of a tube, that kind of looks like carbon nanotubes.
Oh, like it's going around and around a tube.
Yeah, like
I
it's
see
kind of
that.
like helix kind of shape.
Uh-huh. Cool.
Huh, that's
So
funny.
now, I don't know if this would be useful for anything, but I can tell you this, that if we add up all these terms, it's not going anywhere.
Yeah, it's not
Okay.
going anywhere.
But we would certainly say this is different than it going to infinity, right? This diverges, but it diverges because it oscillates, if you will, or because it just kind of bounces back and forth between a couple of numbers, which is different than running off to infinity or minus infinity. So what would we say? We'd say diverges. In fact, we could use the simple divergence test, and we could look at the limit as n goes to infinity of the terms. So where are the terms going? And you would say diverges, yeah? The terms don't go to 0. The sum can't go to 0.
Okay.
So that's a pretty good question on that one. Let me give you one more. Mostly tonight, I would like you to look at, or this afternoon or whenever, I would like you to look at these geometric ones and see if you can get your head wrapped around the geometric ones. But very quickly after the geometric ones, we're going to end up with some that look like this. Okay, and what's the deal with this one? Not geometric. Right? I mean, let's list a few terms so that we can see what's going on. You get 1 over 1 plus 1. 1 over 1 times 1 plus 1. So 1 over 1 times 2 plus 1 over 2 times 3. That's a times. Plus 1 over 3 times 4 plus ... So how do we get the next term? Well, you don't get the next term. Look, you could get this term by multiplying by 3, but you can't get this term by multiplying by 4 because there's no 2. You follow me? So this is not geometric. Which means what? Well, you can't do anything that we learned today on this one, because today we learned how to deal with geometric ones. So what do you do if it's not geometric? Well, something else, right? And I won't spoil this until Wednesday. So if you want to think about this on your own, you can think about what to try on this one. Okay, and so what do? We get a whole bunch of these series with all kinds of different formulas, some even with trig in there or whatever. And then we say, where are they going? And what we notice is that some of them fall into classes or categories. Like some of them turn out to be geometric. And then we can use a technique for getting sort of all the geometric ones. But then some of them turn out to be not geometric. And then what do we do if they're not geometric? We have to do something else. Okay, and so we spend some time, just like we did for integrals, right? How do we do the integral? Well, some of them we memorize. Okay, and then some of them we get because they're related to other ones. We can do algebra to turn them into ones we already know. Okay, and maybe that'll work here. And then, you know, we have all those different techniques for integration. Same thing for figuring out convergence of series. Okay, questions? What do you think this one's doing? Does this have a chance to converge? If the terms
Yeah, I
are
mean-
going to zero, right? Are the terms going to zero?
Yeah.
The terms are all going to zero, so it's got a chance. So what would you do? Well, what I would do is this. I would just do this every single time. Just put it in here and see if I can see where it's going. Once I know where it's going, then maybe once I know where it's going, then maybe I can prove it's going there. Sure looks like these are going where?
1.
Looks like they're going to 1 again. Okay, looks like they're going to 1. So the question is, all right, can we prove they're going to 1? And the answer is, I don't know, maybe you'd start with a simpler one. Well, what about that one, right? What are those doing?
It
And
looks,
that's a little harder to tell, isn't it?
I think you need more terms, but it looks like it's getting bigger.
You want more terms. Okay. Here, I'll put 1,000 in. What do you think? Yeah, it's
Yeah.
definitely slowing down, isn't it?
Yeah.
But the question is it slowing down enough to level off? We're going to take a look at this one. We're going to take a look at this one on Wednesday as well. Okay, so maybe you would look at this one up here, the one that we just did, but maybe you'd also look at this one. Maybe you look at this one first. This is a good one to explore. This is another good one to explore. I mean, that one's even easier. This one we should be able to figure out. If we can figure out this one, then I'm kind of thinking we might have a chance at this one.
So
Okay.
we're still kind of going over 11.2 on Wednesday.
We're still in 11.2, I'm afraid.
Okay.
Okay, so what do? We just got our heads wrapped around, like, what's the game? How do you play the game? And that's basically, I give you a series and ask you where it's going, and then you try to figure out where it's going and then prove it. Okay, that's the game. And what we did is we just looked at some in general at the beginning just to get our heads wrapped around it. And then today we looked at a special class of series called geometric series. And it turns out that if they're geometric, we can figure out where they're going, which is awesome. But then there's a whole bunch of series that are not geometric, like these ones. And I don't know, we didn't have time to look at those today. So we're going to have to look at those on Wednesday. And then I think we'll have most of 11.2 done. I think we're about a little over halfway, maybe 2/3 of the way through 11.2. So you should be able to attack a few more of those problems now. Questions? No, I got 2 no's and I got silence on the chat. I'm going to let you guys go. I will get to your take-home tests as quickly as I can. Hopefully, maybe start them today, get them done before tomorrow, maybe. So they should show up online for you. Otherwise, you guys keep chipping away at the homework in WebAssign. And if you get stuck and need some help, write me an email. Okay?
Sure.
All right. Have a great day.
Alrighty.
We're going to see you guys on Wednesday.
See you Wednesday.
All right. See you then.
Yep.